Alright guys, let's get going. A few things before we start. So you got my message about Friday. I'm sorry, but I really need to take care of this. It's up and down. Some days it's painful, some days it's not. So I need to really find out what it is. Probably nothing special, but my wrist has to go back to working. So we're doing okay with the schedule. If you look at the syllabus, we are exactly where we need to be. I want to finish Spacecraft at Motion today. So for Friday, if you want, your assignment is watching that video, which is a seminar from last year that talks about different things, but the technical focus of that presentation is spacecraft rate motion and control of two satellites using atmospheric differential drag. So at this point, you may be able to follow most of the discussion there, even though there is Lyapunov, nonlinear control, and other things that you may have seen or not. But I think you will grasp the majority of that talk. So it may be interesting to you if this is the field you want to take. That's one. Two, given Friday, and given the fact that in particular the person at NASA who may be hosting us or not, I haven't heard back. So the 14th was a date that I picked, but I wasn't even sure about it. So I will let you know. I would rather not cancel even more classes and go another day. And definitely wait for that gentleman to tell me if he's available, because that will make a difference, in my opinion. So that is still moving around. There was a question last time on linearization, and I hope you took my suggestion to prove to yourself that this function, let's see, we had something like a normal radius of chief plus x over radius of deputy squared, cubed. So the linearization of these, we took the partial of this function, f of x, y, and z, because it's really a function of everything, since Rd is down here. We did this, right? But as someone commented, we didn't do this, and I just told you, believe me, these two, once you compute them and plug in x, y, z, etc. equals to 0, they just go away. I hope you've done that. It's a pretty simple exercise. But you know, when you take the partial of the numerator with respect to y, that is 0. So that term goes away. When you do the partial of this with respect to y, that is that will have a y appearing, and when you plug in the 0, that term also goes to 0. Same for z. So bottom line is these two partials, when you compute them in the point of linearization, which is the origin of LVLH, they go to 0. Just do it as an exercise. It's really not that complicated, but I wanted to respond to that question a little more in details without doing it, because it's the same partial that I've done, except instead of doing it with respect to x, you do it with respect to y and z. Now, I said last time these equations we derived, the Croisi-Wilshire equations, which we put in state space form, right? We said they are linear time invariant equations. I can write them this way, and we did find out what this is, and eventually you may have some control, why not? We do know what this matrix is. So let's say that for now we care about free motion, no control. That's the first thing you do when you have differential equations. You look at the unsolicited dynamics, and natural dynamics, unforced dynamics. So let's say that that's gone. Well then, I said, well, I do know a solution for this system, given an initial condition. The state at times t is equal to the exponential of matrix A t times the initial condition itself. And recall that the state in this case is relative position in LVLH and relative velocity in LVLH. Now, this comes from other classes, how to do this. It's a time series. There are techniques to compute it, but Matlab does it for you, which is what I'm going to do. So I'm going to show you how this solution looks like. This is an analytical solution. Do you have any questions at this point? Okay? Which means if I give you 6 numbers for this state vector and I ask you what's going to happen at time t, whatever you want, you don't need to numerically integrate these differential equations. You can. I'll show you the comparison, but there is no need because it's closed form, and that's the beauty of linear equations. So I'm doing symbolically that exercise in this file, which is already posted along with the CW differential equations that I use at the end to compare right here. This CW equations file is also posted. So these two are posted. So what I'm doing here is I define a bunch of symbolic variables in Matlab. Everything that we have basically seen, omega or OM. I know that if I highlight this, it doesn't look that great, so this is probably better. Is basically a real symbolic variable that represents omega. This is time. This is the matrix A. This is the full state, capital X0 at initial time. And these are the individual initial conditions, X, Y, Z, dot for X, Y, and Z. And what else? I think I'm doing this twice, I'm sorry. It doesn't hurt. This is the actual state at a generic time. And these other variables, I'll define them in a second. And then capital X0, the initial state is the 6 X, Y, Z, X dot, Y dot, Z dot with the 0, because they are the initial conditions. So A is what we have discussed when I derived, well, even before I derived those equations, right? 2 lectures ago, I gave you those equations, and I put them in state space form, and to do that, we assembled A, so that's what it is. Bunch of 1s in the first 3 rows, and then 3 omega, 2 omega, minus 2 omega, minus omega squared. And that instruction down there, except from the simplifier that I always try to use in symbolic Matlab, because it gives me the illusion that the solution is simple, still ugly in most of the cases, but I use it. This is really what I'm doing. I'm doing the exponential of the matrix A times T. Everything is symbolic here times X0, which is this 6-component vector. Okay? So if you run that, you get 6 symbolic equations for the state, which should be my workspace. So the first 3 are X, Y, and Z, given an initial condition and a desired time. So if you give me 6 numbers for these variables at time 0, and you want to know what those 6 variables are at a time 100 seconds, these are the analytical solutions you get. So the first 3 again are X, Y, and Z at a certain time, and the last 3 are X dot, Y dot, and Z dot at a certain time, in closed form. So you don't have to integrate between time 0 and T. Is that clear? Should be. A few things to say here. If you notice, there's a bunch of sines and cosines, of course, all over the place. So these are periodic equations for the most part, with period, the orbital period, because that's omega right there. You know the sines and cosines. There's nothing else. I don't see a 2 omega or 3 omega or other types of frequencies. And on the second equation, is there something that you notice that is different from the other ones? So if I have a function of time that is the x, some a cosine of omega t, and then the y. It's not the case here, I'm simplifying, I'm oversimplifying, but say that this is what I have, right? In an xy plane, without being detailed at all, what kind of trajectory do you expect? Open, close? Should be some kind of closed trajectory, right? If A is greater than B, it will be something like this, for example. It could be, right? But it's definitely not going to be something like this. Correct? Okay. So that could be the case, looking at those ugly equations right there. By the way, you can compare this with what you have in your book. They just use different names for the variables, but they look exactly the same if you pay attention for a couple of minutes. Well, the second equation has something going on, though, right here and right here, which is 2 linear functions of time. And that's the y solution. Okay? The other ones don't have that. So something is going on in the y direction. What could be going on in the y direction? What do you think? We always have to remember what's going on here. I have planet. I have the chief. This doesn't want to be a polar or equatorial or whatever orbit. It's just an orbit around the planet, okay? But definitely it has to be circular, because that's the assumption behind those equations. Otherwise, they don't work anymore. So at any particular time, the chief is somewhere, and we have defined the LVLH basis, x, y, and z. Yeah, I'd say that it's pointing at us. Why not? I'm looking at the y anyways. If the deputy, just as an example, if the deputy is actually as well in a circular orbit, okay, so this is the chief, this is the deputy, D. If it's also in a perfectly circular orbit with a slightly bigger same major axis, what do you think is happening from this guy's point of view? Because I'm sitting there right now. Those equations are based on being with the chief, attached to its coordinate system, and looking at what the deputy is doing, right? So remember that the first three functions there are telling me how the projections of this raw vector evolve with time in x and y. So if the direction of flight is, say, counterclockwise, why not? For both of them. What is happening to the deputy? Is it flying faster? Is it flying a little slower? Faster? It's going slower, right? Higher orbits, lower velocity. Remember the circular velocity expression. So it's going a little slower. So even if at some time you have them aligned with the RC vector, right? Deputy is right here. Over time, it will, from the point of view of the chief, it will drift away, right? It will fall behind. Remember the phasing maneuvers? So, and likewise, if the deputy is actually in a lower orbit, from this gentleman's point of view here, the astronaut on the ISS in circular orbit, the deputy is actually going ahead. It's going to, over time, increase its y position. So the fact that I have a term that is linear with time could make some sense. I could see the y diverging, and that's actually what happens. If you just put two satellites in circular orbits, I should close my Outlook probably. Two satellites in perfectly circular orbits where there's a slight difference in radius at this point, because they're just circular, there will be a drift, right? Different same major axis, there's a drift. So those linear terms, they look like, let's just collect them. Let's see, I have a minus 6, look at the first one, omega, it's multiplying x0 that is outside of the parentheses in front, times t, so t will be for both of them, okay? Minus 6 omega x0 t, and then the other one up here, so this is the first term, the second one, it's a minus 3 omega y dot 0, right? So they both multiply t. So you can actually get rid of that by imposing that this has to be equal to 0. Why not? Now, since time is time, can't force it to be 0. You can if you say now it's time 0, but then it will keep going. Unfortunately, can't control that. So this is the one thing that I can try to modify. So if that is always 0, then I get rid of the linear part, of the drifting part, okay? Of this component of the motion that separates the satellites over time. One way to solve for this is saying that y dot at time 0 has to be equal to minus 2 omega x0. This is the most well-known equation in spacecraft relative motion where people talk about Clausius-Wilshire equations. That's what gives you a periodic relative motion. In other words, you don't see this rho diverging. You don't have that nonlinear diverging term anymore. These objects will move with respect to each other in a closed path. So the relative trajectory is closed. Does it make sense? In the most general case, it is not. So if you look at only x and y again, forget about z, z is a double oscillator. If you look at the x and y motion, in the most general case, it is not a closed trajectory like in this case, but it is a combination of sines and cosines plus the linear term, such that in some cases you may see, let's see, this is, can I do this? X is radial going away from the planet is down here, and y is this way. It looks easier. So say that your deputy is a little higher than the chief, well, it will drift away in which direction, we said? Right or left? This is plus y, for example. It will fall behind, right? But the actual trajectory will actually look like this. Because there is that linear term that drifts away, but there's also sines and cosines, so there's some oscillation. In the other case, it's going to look like this. It's going that way. And out of plane, again, it's just a spring behavior without any damping. We know that because that's the differential equation for the z motion, and that's exactly what you get right there. So they are very interesting equations. You can get something closed, so something, for example, centered around the chief that repeats itself only if this condition is satisfied, which matches, from an inertial point of view, what condition do you think that is actually expressing? If you think about orbital parameters, what do you think is happening between the two orbits? This is all Keplerian, perfect ideal, motion, not J2 for now, there's nothing else. So both the orbits are perfect. They don't change plane with time, there's no change of RAN, there's no change of inclination, nothing. I'm only looking at two perfectly Keplerian orbits, but what do you think happens so that the two satellites don't drift away from each other? Other than, that, but from an orbital parameters point of view. Same semi-major axis. They can have, the chief can't have any eccentricity, right? If I'm still working on these equations, forget about that. Chief, I said, it's a circular orbit. The deputy could have eccentricity, but if he has the same semi-major axis, they should, the motion for both evolves at the same frequency, right? Same semi-major axis means same orbital period. They go around once in the same time. So eventually, whatever happens in these bases is going to repeat itself. Okay? All right, I hope I convinced everybody, because I need to move on. So that is the first thing to observe. Now, another thing to observe is, well, we'll continue running this. Let me skip. Okay, yeah, this is a good. This is a good example. This is exactly doing. So forget about these lines here. We'll go back to this. This is for an impulsive maneuvers. So let's say that I found the analytical solution, okay, and then I'm going to run a numerical example. I have omega 0.001 radians per second. I think the ISS has more or less that angular velocity. That is the corresponding orbital period. And I'm picking just some initial conditions for radial position. See, these are kilometers, 5, 2, 1. They're far, pretty far from each other. And some initial velocities for x and z. And I am imposing this condition right here, okay? So I should get, hopefully, some closed trajectory that repeats itself. And I am running the simulation for, don't ask me why, 3/2 times the orbital period. I wanted to do at least an orbital period. So what I'm going to do here is approaching the problem in two different ways. I told you that I have an analytical solution, so I can just this is 1,000 points between initial time and final time. At each time that I desire, just run the analytical solution. Time 10 seconds, this is position and velocity in LVLH. At time 20 seconds, this is position and velocity, and so on and so forth. And you create these points without any OD45. So that is what this instruction is doing. The t equals lean space is just creating a bunch of time values, and then with this instruction, I'm actually creating all at once. You can do that in Matlab, the power of Matlab. You can create the corresponding x, y, z, x dot, y dot, z dot for those times, okay? You have this function, it's posted already, so you can play with this with a little more time than the 15 minutes we have. So that is one way that I can create x, y, z, etc. And I plot it, and then down here I'm actually integrating the equations of motion because I want to. So I have a differential equation, CW equations, this one right here, pretty simple, that does implement those three differential equations. And so if I run these all the way to the end, let's see what happens. Okay, so The red line is just a projection in the xy plane of the actual trajectory. So the blue line is what you see in 3D in LVLH. So that's the x LVLH, y LVLH, z LVLH. You can move the axis around as you want. And those are initial and final time steps that I've chosen. It is a closed ellipse. Make sense? So if in particular you go, let's see, you want to see, yeah, let's start with xy. That's what you get. The fact that I have red is just because I have plotted only the x and y on top, but you can remove that. And then you can see all the other planes if you wish to. Okay. Now, if I don't do that, say that, I don't know, I am picking random numbers, so I have no idea what is going to happen, but I don't want this special condition anymore. I don't think the orbit is going to close anymore. Yeah, it doesn't. So it's drifting. And if you go in the xy plane, you should be able to see that. It's drifting in the negative y direction. Okay? Yes?
So the previous graph you had, they were not drifting.
Mm-mm.
There was an eccentricity difference, or not, an inclination difference between the, so even with an inclination, you can still have no drift.
Yeah. In Keplerian, yes. The next example, that doesn't work anymore. If J2, yes, it doesn't work anymore. But with perfect Keplerian motion, which is, again, your only acceleration is this. Yeah. Basically, the outer plane doesn't explode. It repeats itself. The only thing that can make the drift is the outer plane. Different same major axis. Yes. These are only CW equations, by the way. This is not the nonlinear reality, okay? Any other questions on this? So the next step now is, these are linear equations. I can do a lot of stuff with them. So the other thing I can do is, if you look at those analytical solutions I computed in Matlab, you can also organize them in the following way. You can say that your state x, y, z, x dot, y dot, z dot is equal to a big matrix of 6 by 6 components, etc., okay, times that initial state. Agree? And what is this? Well, that's we've seen it before. This is the exponential of AT, right? So what I'm calling at line 39, I'm calling this phi, and it's called the state transition matrix. It's what transitions your state from a certain time to another time. Make sense? You give me the state at time 0. I'm calling it 0. This could be any time. It doesn't matter. You can map with one instruction a matrix that multiplies this initial condition to another time. In general, if you really want to be thorough here, you can have t minus t0, okay? So this may be clearer. This is the state at some time t0, and this is the state at some time t. So one thing that I can do using this is the following. I look at this matrix. There are 6 by 6 components in here. I will break it into smaller matrices. And in particular, I'm going to call this one here, this 3 by 3 first piece, phi RR, because it connects position with position. You see that? And then I'm going to call this phi RV. because it gives me x, y, and z, and it's the part that multiplies velocities. Now, say that now I want, for some reason I want to actually rendezvous. I want to go to 0. So what I'm actually doing right now, without saying it, is a 2 impulse. We've done this with Keplerian orbits, so we'll do it here again. 2 impulse rendezvous. So I started from some given initial conditions. My satellite deputy is in this particular configuration with respect to the chief. I don't like that. I want to go to the chief. I have to dock with the chief. I am the shuttle and I need to dock to the ISS, and I want to do it with 2 burns, for example. So this is given. And I don't want a generic final x, y, and z. I want these to be 0, 0, and 0. And how do I do that? Well, I take these 3 velocities that I'm given, and I apply a delta v. I'm going to change them so that the resulting position, final position, after a certain time that I decide, is going to be 3 zeros. In other words, I want those 3 down there, x, y, and z, I force them to be, after a certain time, 3 zeros. Well then, x, y, and z in general, if I break the matrix, state transition matrix that way, I can write them this way. Phi RR, x0, y0, z0, plus phi RV, x0 dot, y0 dot, z0 dot. I'm just rewriting this expression in using these 3x3 and 3x3 matrices, sub-matrices that I decided to define. Okay? Well, so my goal here in this equation is set this to 0, right? I impose this to be 0, and solve for this, which would be my new velocity. My real velocity would be whatever I'm given in this example was these 3 numbers. I don't like that. So I want to compute what the velocity would have to be at this initial position to go after 100 seconds, whatever you choose, to end up exactly at 0, 0, 0. Are we following? I'm inverting this equation in terms of the desired velocity that I will have to have. And then how do I create that is with an impulse, for example. You just change the velocity of the deputy. Remember, we're maneuvering the deputy here, not the chief. If you fire a thruster on the chief, it's not circular anymore, probably, so you don't do that for these equations. So I'm going to solve for that, and the solution is pretty simple. This is a bunch of zeros. You move this to the left, invert this matrix, you get x0, y0, z0, dot, 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 and I'm going to call this, if you want, new, just to make sure that we understand this is what I have to obtain to go to 0. Well, this is equal to minus phi RV inverse times phi RR times the initial position. Sorry, this is overlapping. Okay, so this is what you would have to obtain at this particular state of the deputy in terms of position to end up at 0. And the time, remember, time goes into these matrices here, because these matrices are those cosines of omega t, sine of omega t, they contain all of that. So your chosen time to get to rendezvous is a parameter you pick, and obviously if you want to do it faster, your delta v will probably be higher, and vice versa. So this is exactly what these lines are doing. The phi matrix was that exponential of AT that I computed analytically. The phi RR is the first 3 columns and rows, and then the phi RV is the first 3 rows and last 4, 5, 6 last 3 columns. And symbolically, this is the delta. This is the new velocity you would have to have. So the inverse of phi RV, here it is, times phi RR times the initial position. That is the new velocity you would have to end up at 0. So let's verify that that's true. I'm going to comment out this, because this is exactly, these 3 lines of code, and again you have all these, this is exactly copy-pasting what val 0 new gives me symbolically. So if I run this again, these 3 expressions, it's exactly what I copied down here, except now I'm going to have numerical values. So I'm going to finish running this, and hopefully the trajectories will go. You know, I think I can get rid of. Yeah, I don't like these. You've seen the z is going to 10 to the 15th. That's probably not a good idea. So this initial velocity I have, I'm actually going to put it back to what it was before. Why not? There's nothing wrong with that. So this will probably look a little better. Yeah, that doesn't matter because I am changing the velocity. Let's see. It's the initial position that is big. Anyways, there's nothing wrong with this. I'm just trying to avoid that 10 to the 15th, but yeah, it wants to stay there. You can play with this. It's just a choice of initial condition. It is what it is. So let me remove the red one. I don't want to see that necessarily for now. Come on, go away. Doesn't want to go away. All right, so let's do this XY view. Okay, at least I can see it from here. So this is what I started from. And I have taken my initial conditions, these ones here. I ignore the velocity, I change it to whatever it needs to be to get to 0, and it is going to 0. As you can see, it's going here. So in practice, what do? You have an initial relative velocity with the respective chief. You compute the new velocity, the difference of the two is your first delta v right there. And then down here, I am going to be at 0, 0, and the same for the z. But I'm going to have some residual velocity. That's probably what happens, right? So the second delta v, that's why it's a 2-impulse delta v. It's just equal and opposite to whatever is your residual velocity. If you approach the shuttle pretty fast, you will have to oppose the velocity with the last delta v, and you are matching also the velocity. So that's what we do with classical Schreier equations. That's what we call a 2-impulse rendezvous. Start from an initial position, x, y, z. With that, compute what the actual velocity has to be. This will guarantee that you're going to be at 0, and then correct whatever residual velocity you have at that position. Yes?
That bottom equation up there, that would only work if you're going back to the chief, if x, y, z all equals 0?
Yeah, but you can leave something that is not 0 here and solve that too. Yep, absolutely. That's a good point. So this will work to go to any other point because they're linear equations. So every mapping between an initial state and a final state is all analytical. So you can, that's another good exercise you can do probably with this same code. You can tweak it so that these, now they're not zeros anymore. There's some other point you want to reach and try to find what your new velocity has to be. Make sense? There's more to say. Do you have any questions on this? So the code you have to, basically these are the three lines to comment and uncomment. If you leave these 56 through 58 uncommented, they will give you a modified velocity and the trajectory will always go to 0. By the way, one thing that I forgot to say here is that there are overlapping trajectories here. I completely forgot about that. I am plotting twice the same trajectory, one with the analytical solution and one I didn't close the plot. I think it's just plotting on top of it. And one with the numerical integration. So if you go under the blue line, I think, let's see, what am I doing here? Yeah, there's trajectories on top of each other somewhere. Oh, down here. Yeah, blue. So the blue that you see is the one from CW equations. If you're able to select this blue trajectory that doesn't want to do for me, there should be another trajectory just below this one. This is exactly the same. Yeah. So the black one is the one that I obtained with the analytical solution, just sampling every so many time points. And the other one was with the integration of CW equations. And they better be the same. of course. Now, for the delta V's, what do you actually do? What happens in the inertial world? What do you think? Because what I'm telling you is basically the deputy has whatever initial velocity it has at a certain time, right? Okay. But I don't like that, so I'm going to change it with a delta V. But this is based on CW equations, right? I'm going to change it doing this. Right? That's basically what I'm doing. I need to add, remove, do something to the velocity so that I go from whatever I was given to this new one that will drive me to 0, if that's what I'm trying to do, going to rendezvous with the chief. What do you do in the real world? Well, nothing really changes, but it's good to know that. So we have, the condition is the same. This is ECI, right? And we have chief here, and we have deputy somewhere, RD, and we call this little vector rho. Well, the velocity of the deputy is the velocity of the chief, we know this, plus, I'm going to call this VREL, or I can just call it rho dot. Actually, rho dot is probably the best. No, it's not. Let's call it VREL. Plus omega LVLH ECI cross with rho. This is the transport theorem. This is actually rho dot. This is how this little vector is seen changing over time from the ECI point of view, while this VREL is how rho is changing in LVLH. Little x, little y, little z, whatever they're pointing, okay? This is the three x, y, and z dots that I've carried around all over the place. Do we agree on this? So the velocity of the deputy can be expressed this way. It's the velocity of the chief plus these additional terms. And it's just, looking at this triangle of vectors and applying the transport theorem for little rho. But, this, you can imagine that this is happening twice before and after the burn. Say that, I don't know, before the burn I have V deputy prime is equal to V chief prime plus V rel prime plus omega LV LH with respect to ACI cross with rho. Now, is this going to change? Is this going to change? Is this going to change? No. If I do an impulsive maneuver, first of all, I'm not going to maneuver the chief, I said that, right? Don't touch the chief, otherwise it's not circular maybe anymore. So this is not going to change. This, yes, the angular velocity of, this is based on the chief, and that's not going to change. And it's an impulsive maneuver. By definition of impulsive maneuver, I am instantaneously, magically changing my velocity without affecting positions. So even the rho vector is not supposed to change. So so this is before the burn, right? B, before, and after the burn, I have VD second is VC plus VREL second plus, this term is the same by definition of impulsive burn. So, the bottom line is that you subtract the two and the delta V's are the same. Right? So the amount of thrust you have to apply to the deputy is what you would do from an inertial perspective. There's no difference. So if you compute the delta V this way, that's how much fuel you actually have to use for the deputy. The only thing you may want to do is change reference. If you don't like these expressed in LVLH, you want an ECI, you have to do a projection. But that's just changing basis. But they are the same amount, which is good to know. We're not done. We're almost done. Uncollected homework 9. You really have to do this one. It's right here. So I'm giving you a chief and a deputy and their orbital parameters. They have the same major axis. The deputy has a little bit of eccentricity. Okay? Same inclination, same RAN, same argument of perigee, and yes, a slight difference in true anomalies, 0.001 degrees. So I'm asking you to do this. Well, the second point is CW equations, and that's what we have seen. The first point is look at the relative motion, only in the xy plane, by the way. I just want to know how x and y evolve with time. But do it in two different ways. One is with relative motion, directly from the integration of the equations of motion. So the first one, you integrate basically twice the equations of motion for these two guys. And what I suggest you do, you convert these orbital parameters into a state vector and do it with ODE 45 as we've always done. So you have that function already. So basically convert orbital parameters into ECI coordinate systems, x, y, z, x dot, y dot, z dot, integrate independently. And then what do you do? How do you, once you have a bunch of positions and velocity in ECI for both satellites, what do you do? I lied, they don't have the same major axis, sorry. Yeah, slightly different major axis, that makes sense. I was thinking about the plots that I had in mind, and yeah, they are actually drifting, and that makes sense, okay. So what would you do once you have a bunch of positions for the deputy, a bunch of positions for the chief, and then the corresponding velocities? What do? I want now xy in LV, LH. I'll show you through Matlab because I think that's a very good way of doing it. Well, this is repeating what I gave you, chief orbital parameters, and I'm converting, so everything that you see all the way to 62 is converting into Cartesian coordinates. So nothing new, you have that already. Same done for deputy. You have that already. So all the way to down here, there's no surprises. These two groups of instructions are integrating in Cartesian coordinates the equations of motion for chief, deputy. No surprises. You just have two now instead of one satellite. But you have a bunch of positions and velocities for chief and a bunch of positions and velocities for deputy in ECI. I'm asking you at point 1 to look at what happens in LVLH, because you can do that. You don't have to look at CW equations. You could actually look at what's happening from direct integrations of the equations. So what I'm doing in this for loop is exactly that. This is the x direction of LVLH. Everything is based on the chief. So the I LVLH at each time step is wherever the chief is over its norm. Right? That's what we do, right there. The J LVLH, it's kind of an abuse here, but I do know that it's in circular orbit. I suggest, so the way I'm doing it here is not the best. I would probably first compute the angular momentum of the satellite, define k in the direction of the angular momentum, and then cross the k with the I to get the j. But here, I know the chief is circular, so I'm just directly defining the j, because the j is not necessarily aligned with the velocity at all times if you don't have a circular orbit, right? But anyways, in this case it is, I know that. So the j in this case, I'm just saying it's velocity of the chief over its norm. Again, keep in mind, this is true if it's circular. If it's not circular, don't do that. Just go through k first and then cross. But anyways, I can do it. So I have these two directions defined. What I'm doing here is, forget about this for a second. What is little rho is the difference of position vector of deputy and chief, right? But if I just do that, it's not projected in a VLH. It's still in the ECI basis, right? If these two that you have obtained through numerical integration are expressed in ECI, that's not what I want. So little rho, that is deputy minus chief, if I just do it like this and don't change the basis, I have it in ECI. That's not what I'm asking you. You have to do it in ECI. So this instruction in front, multiplying times this matrix, it's a rotation matrix that we have seen in other Matlab code, probably, for orbital parameters, if you recall. So all this is doing is taking this vector, which is little rho, this vector is little rho, is just projecting it in LVLH. And this is the relative velocity. I erased the equations before, but before doing the projection, this is what I'm doing. Velocity of the deputy minus velocity of the chief minus the cross product of omega and little rho, which I have computed at the previous step. So, what it's implemented in the line of code is the following instruction. VREL, the matrix in front is just projecting in the new basis, but really VREL as a vector is velocity of the deputy minus velocity of the chief, those two there, minus the omega of LVLH ECI with respect to ECI, which is crossing rho. That's what I'm doing right there. Make sense? Silence means yes. Okay. So all this for loop is doing is taking the position velocities of those two and making them appear into LVLH. And then I integrate and then of course at first time step that would be the initial condition for relative position and velocity. So you can plot those, or you can take that initial condition and just integrate the equations of motion, the linearized ones, the classical shared equations, which is what I'm asking you to do as point 2. Use the initial relative position and velocity that you still have to compute the way I just described to integrate the CW equations and see what's going on. I do not recall the conditions I left on. Let's see what happens. So you do not have this code because you really have to do it by yourself. And I hope we understand each other why I think you have to do it by yourself. So this is the outer plane part. To respond to that question before about the Z motion. Basically CW equations or nonlinear motion without J2, the Keplerian dynamics, they behave the same way. That's a 10 to the minus 11. It's basically, I started on the same plane, they remain on the same plane. There is no reason why two Keplerian orbits have to go out of plane if they are initially in the same plane. There's nothing pushing them out of that, right? If I only have pure Keplerian acceleration, there's no drag, that is not going to change the plane anyways. Not J2, nothing. So nothing changes in the Z. This is instead how the two approaches compare each other. Let's see. The blue trajectory is the real LVLH x and y. This is only in plane, right? X and y. This is away from the planet, and that's direction of flight for the chief. You see, they are on top of each other. The CW equations is the red trajectory until they start diverging because they are linearized equations. They can't hold forever. If you don't keep them close, they will look different. And a very interesting that I've done, and that is the last thing we want to look at, so do this homework before next week, for sure. What if I have J2? Now, these equations are modeling, first of all, only Keplerian motion. That's how we derive the CW equations, and the chief has to be in circular orbit. There's no J2. So if I add J2, I expect even worse approximation, right? Something else that I'm completely ignoring in the derivation of those equations. So hopefully they will diverge a little quicker. So you can also do this as an additional exercise. The first thing we notice, that idea of the outer plane motion, they were in the same plane, they remain in the same plane, is not valid anymore. It's valid for a while, but then as time goes by, this is 10 to the 4th, so these are 10 hours if I'm not mistaken. Eventually, the nonlinear world with J2 that is actually affecting both trajectories is going to start creating some oscillation out of plane. They're not remaining in the same plane anymore. And the divergence in the xy, if you compare, if you recall the previous plot, the divergence starts a little sooner in terms of relative distance. They start looking different before, because this is an additional, not only I'm not taking into account no linearities, I'm completely ignoring J2 here. My equations did not model that at any point. Is this drinking from a fire hose? Probably. Too much stuff? Think about it. Play with the code I gave you. Because it's really mostly linear equations. The difficult part is there is 6 of them at the same time in matrix form, but they're all linear equations. All right, thank you.